Okay, everybody, it is 3:30 and time to start. It's my pleasure to introduce here. Known you since 13 years. Now I just figured out how to pronounce her name today. She came here after graduating with a PhD from the University of Illinois, and if you look on her seminar abstract, there's a list of all the awards she won. I'm not going to repeat that because I want to give her time to give her seminar.
Thanks, Jim.
Thank you. Thanks everyone for coming. So today what I wanted to do is talk a little bit about some of the work that we've been doing in the lab connected to learning and manufacturing systems. For many of you, these first two slides aren't going to be that relevant, but it's a quick overview of kind of what we do in the lab, just to give people a little bit of perspective of where we sort of are coming from and some of the other things that we do. So we primarily focus on modeling, sensing, and control within the group in order to develop robust and reliable systems. So we have kind of three core areas. We look at cooperative multi-agent systems, we do planning and control, and we also think about modeling and data analytics. And those are kind of our three core spaces and the intersection of them. And within that, there's lots of stuff we do kind of from the more theoretical perspective. A lot of it tends to be more on the control side, where we're thinking about how do we do learning-based algorithms, how do we think about these distributed systems, and so on. We also have a lot of tools that we'll pull in from different areas, optimization, machine learning, different kinds of modeling techniques that we get to kind of apply and work with along the way. Now, what we do is we actually have a pretty broad range of applications that we work on in the group. And so I've sort of loosely coupled these into a couple of different core spaces. The first is that we work in cooperative robotics. This includes human-robot collaboration. Actually, Minji's here today. He's up on the screen for us. We also do robot-robot collaboration, and we also think about things like task allocation, mapping, and planning. So those are all kind of in our cooperative robotics space. We also have a fair bit of work in the energy optimization and control areas. And so within this, we think about and oftentimes collaborate with other researchers in some more of the biomechanics, and we're looking at energy use of humans as well as other biological systems. And then we also think about how do we take some of these application spaces that tend to be more on the energy side and try to think about designing control strategies that'll optimize energy harvesting or minimize energy use, things like that. And then lastly, which is kind of the subject of today, is the area broadly of manufacturing. We do this both from kind of a systems level, but also a process area. A lot of work in multi-agent decision-making, this whole concept of digital twins, and then primarily what I'm going to focus on today, which is in the space of additive manufacturing. So the work that I'm going to present today comes from a lot of different folks who over the years have helped contribute to different aspects of this. Many of these are actually former PhD students or postdocs who were in the group. Some of these are collaborators that are both international, but also at Ohio State. So I wanted to acknowledge that they're part of really this body of work that I'm presenting. Okay, so I'm going to start by giving sort of an overview of why we're interested in learning and manufacturing and kind of how we're going to frame our problems in that space. Then we'll talk a little bit about a case study and how we've come to sort of think about introducing learning into manufacturing and sort of finish up. Okay, so to start with, I think it's important to get everybody on kind of the same page. So when we think about learning, what we're really trying to do is we're trying to come up with the ability to derive a new understanding of a system using information about that system. And we want to then use that to enhance our ability to make that system behave in a particular way. Okay, we're going to focus on manufacturing for this. When I say system, the information that we can be getting, this could be information that we get from the resources within the manufacturing system itself. It could be from an operator or a subject matter expert. It could be something from the environment. It could be information we're getting from other systems in that space. Okay, so we want to be able to sort of take all of that knowledge. And when I talk about the information, I mean a bunch of different things here too. So that could just at its broad sense, it could mean sensor data. Obviously, that's a lot of what we'll be dealing with. But it could also mean the physics that are sort of being used to describe these systems. And it could be historical data that we're going to use to then create a new different type of model. And all of this is so that we can kind of apply these two things together so that we can update our understanding of what's happening. And oftentimes then we translate that into some kind of decision that we can make. So that might mean that we change something about our model. It might mean we change something in terms of our reference signal or an input we're going to send into the system, or the controller itself. So all of these are sort of areas where we're open to adapting them. It just depends kind of on what our initial objective was and how we can enhance our system performance. So learning is not new, right? This has commonly been used in manufacturing before. Data-driven modeling is a kind of a nice example of where you think about taking, essentially system identification, right? You take data that you collect from your system, you use that to come up with some kind of interpretation or representation of your system dynamics. So we can do that in different ways. We can use regressions, we can use neural nets, we can use a lot of different techniques to just sort of focus on the data side to help us understand something about our system. We also see learning a little bit more from the control side as well, where we can have some sort of more common methods are examples like iterative learning control, where this is an idea where we use a batch sort of process, and that means we're going to do something and have an initial reset. We can also do it from a repetitive control perspective, where in that example, we're assuming that we're continuously doing something. And so our output at the end of one cycle is really our input to the next. Okay, and that's kind of how those two are separated. But these are established techniques that folks use in many different domains. So why, again, sort of are we interested in this problem? Well, some of the reasons are that as we are seeing sort of this push in manufacturing, there's part of what folks are interested in doing is making these systems more flexible and agile. So they want us to be able to adapt to disruptions or new product or customization, which means that we have to have a strategy to handle this and make our control or our understanding of the environment more flexible. Also, we're seeing this push in advanced technology, and what that generally means for us is that we are going to see faster dynamics. We're going to see a push for higher resolution. So this is really taxing sort of our sensing capabilities. We're going to see applications where we have multi-materials and multi-phase dynamics. That comes in kind of from the modeling side, right? How do we think about capturing some of this behavior, and what do we need to capture so that we can make a smart decision? And then the last piece is kind of connected into that modeling side, which is that we have multiple domain dependencies. And so we're not just trying to solve a problem that sits nicely in, say, the time domain, but it's generally something that's coupled with time and space and potentially even a material phase change. Okay, so all of these kind of create challenges from a modeling and control standpoint. So when we think about learning, there's some advantages and some challenges that we've kind of come across and sort of use to help us think about when it's appropriate to use it and when it's not. So from the advantage side, most of the time we actually can get quite a bit of data, right? These are fairly structured environments, which is the next piece. And so with that means that we generally can instrument, so we can get data back. And also because it's controlled, more often than not, we do have behavior that tends to be fairly predictable. All of that sounds good, right? From a controls perspective. We also see a lot of repetitive actions. In most manufacturing cases, you're not trying to create one product, you're trying to create multiples of these. Okay, so all of that is actually very helpful to us from a learning perspective. It means we're going to be able to use those features in that learning architecture and take advantage of that. But of course, there's some things that come along with that. Even though we have a lot of data, it's usually unbalanced and it's generally quite noisy. Okay, also there tends to be some monitoring mismatch. Some of that comes up because we have requirements that are either very high speed or high resolution, and maybe we don't actually even have the sensing capability to do that. It could also mean that what we're interested in is not something we're able to measure. So we have to sort of infer a response. We see a lot of complex nonlinear dynamics. So again, we want to think about what do we need to capture in our models and what could we simplify down to so that we can kind of ignore for the time being. So what's important and what's not, and sort of how do we identify that? And then most of the time there are humans involved in what we're doing. And that can often mean that there's unexpected behaviors or there's just components that we want to move towards to make things a little bit more autonomous. Okay, so towards that, let's take a look at a specific way of thinking about doing this towards additive manufacturing. So we're going to start by looking at some of the challenges that we see in additive manufacturing from a modeling and control perspective. So this is a nice classic example. This is an extrusion printer. We're going along, we're laying down very consistent concrete lines. It takes a long time to get to this kind of capability. And, you know, there's lots of different things that go into this. This is one example, right? So this is an extrusion process. There's actually a lot of different types of additive manufacturing processes. That's one. There's jet-based. That brings its own sort of interesting dynamics into the problem because you're now dealing with liquids, okay? In extrusion, those materials tend to behave in a fairly predictable manner and they don't move around. That's not true with the liquid, okay? The liquids move around a lot more and they create many more dynamics that we have to sort of consider within our process. Of course, there's laser metal printing. That's a completely separate, different type of manufacturing from an additive perspective. It has a powder bed. That's really not what we're going to talk about today. But all of these have seen this huge growth. And what's really interesting about these application spaces is that even commercial systems are, in some sense, they're run open loop, which sounds sort of crazy, but that's actually how they're done. They're sort of over-designed to begin with, and you work really, really hard to come up with what should be the set of process parameters, what should be the inputs I should be setting, how do I make my system really, really, really tightly controlled so that then I press go and it just goes, okay? And that, as anybody who's ever worked with a 3D printer knows, that often leads to things that don't go the way we want. And so that's what we're trying to work on within our lab. So I'm going to focus my example on a very specific kind of process that we do in the group. This is electrohydrodynamic jet printing. This is a jet-based process, so it is liquid-based. It has some nice advantages that we get from this particular process, that we can actually do things in the micro nanoscale range. We can use lots of different kinds of materials. And we can do this with non-planar substrates and allows us to have kind of a broad application space. Most of the time, we're really dealing with sort of the sensor domain. So we're looking at optical sensors, electrical sensors. But that's kind of the reason why we're interested in this process. It is fairly repeatable. It has at least that repeating dynamics, which is what we're seeing here in the video. It is fast. It's not very expensive. And so those are really good things. And what we're generally trying to do is think about how can we use learning and control to improve this performance and make it so it's sort of automated and we don't have to think about doing all that really early pre-processing and design. Okay, so there had to be some challenges, right? Otherwise, it would be a really quick talk as to how we could do this. So when we think about this process, there's actually a lot of process parameters that have to be tuned if we're just going to run everything open loop. And it takes a lot of time to actually get at what each of these should be and to understand the relationships between them. And so that's kind of the first piece that makes it really challenging, right? Is there's all these different parameters that I'm going to have to set, and I need to understand the relationship between them and what I'm seeing as an output. And the reason for that is that if I don't understand those or I set them incorrectly, then the process doesn't behave the way I want. It's a little bit hard to see, but at the start of this video, the system's spraying. You can kind of see there's like a shadow around where I want. As I go along, we're tuning, and we can tune to where we're now laying down a nice consistent line. What we're going for here is a nice thin film. Okay, the spraying that happens at the beginning is not something that we want with this process. And so that's, kind of this example of what happens when we don't get the things that we want. Also, if we set these process parameters incorrectly, we can also see examples like this. So this is a case where what I want is this nice printed connected line. I want this to be connected because I'm trying to print an electronic. Okay, so I need this. This is a conductive material. I'm trying to make this continuous along the way. I think I have my parameter sets right, but what I get is the image on the right. I want to point out that that bar up there, that's a 2 micron bar. I can't see that with the naked eye, right? So I have to have other ways of sort of visualizing this to tell when I'm just printing along, or actually I say when my student is just printing along, they can't see that, okay? So how do we sort of deal with this kind of behavior? And like I said, the problem right now is this is all done open loop. So we need to think about moving away from this manual tuning, moving away from a student or a person having to sit there and manually adjust these, or put this into such an over-constrained, over-controlled environment that it's no longer practical to even use it. So that's kind of where we have this sort of this goal, right? This is what we're currently doing. We have open loop, or this is what most 3D printing processes are. They're open loop, and you have to really work to tune your output. What I want is I want the system to be closed loop. Okay, I want the system itself to sort of figure out what should be doing, and I want to be able to get this nice controlled output. So this example, and I'm going to bring this example up a couple different times. This is a nice thin film. In this current image, it's actually stacked layers. Okay, so it's hard to tell that, but it's nice stacked layers. These layers are about 100 nanometers thick. Okay, and I need them to be very smooth. And I need them to be stacked one on top of each other. Okay. So that's already kind of a challenge, but you might ask the question, well, why wouldn't you just use lithography? It sort of seems like I could just do that. The reason is because this image doesn't tell you what I'm actually doing, which is I'm creating variances in the layer thickness, which is actually coming back and creating different refractive indices, which are showing up as different colors. Okay, so now actually that becomes a very complicated sort of pain in the butt lithography problem. Okay, it's multiple different masks, multiple different layering, and it's not straightforward and becomes kind of a nice candidate for 3D printing, which is much more flexible. Okay, so the question then is, how do we actually get to something that looks like that? And how do I do it without spending months tuning? So that's really what we wanted to do. And the first question that we sort of asked ourselves was, could we just use feedback? And we quickly came to the answer that no, we can't. But let me explain why. Okay. So one of the first problems with feedback for us was that we actually were taking indirect measurements in order to infer behavioral responses. And the reason for that is that what we actually typically want in our outcome is a functional behavior, right? Whether it's a conductive material, so what I really want is to be able to understand the resistance properties of it, or it's that example again where it's an optical sensor and what I really want is this refractive index. That's something that I have to measure generally off my printing system. Okay, so I have to I'm actually going to try to use geometry to help me understand that I'm moving in the direction that's going to give me this nice behavior. And this upper line plot up here, oh, you guys can't see my mouse. In the upper one on the left, the printed line is the thin single line, okay? So that one's printed. The others are actually put in, but with lithography. So that's problem number one, right? And then the other issue about the sensing is that I have very fast temporal dynamics and high resolution spatial dynamics that I'm dealing with. So I can embed things like an atomic force microscope. That's going to give me very high resolution, but I can't do that directly while I'm printing. I can start to do it layer by layer, but that's sort of inducing a pseudo in situ component. I can also think about the high speed, but that's going to lead us to thinking or looking at, can I use a high speed camera? Can I capture that and process that information in time to be able to make a change in real time to my jetting dynamics? So generally speaking, for our case, the dynamics tend to be too fast or too small, or the behaviors that I want, I can't measure directly. Then there's a couple of challenges from the modeling side. I have multimodality, which means that I actually transition between dynamics depending on the inputs that I'm sending into my system, and I see extremely different behavior when I do that. So that's one piece I have to be able to not only understand when it happens, but be able to characterize it. As I mentioned, these are liquid materials. And so I also need to understand how they're going to interact on the surface. Okay, and so when they hit the surface, in some cases, I might want them to impinge and merge together like we see on the bottom, particularly if I'm going to do a film or a connected line. In other examples, I actually want them to stay as separate entities. And so I need to then understand how pitch and resolution size are going to correlate to that. And so I can do some interesting dynamics with that. One other piece about the modeling side is that because these are liquids, the underlying surface plays a big role, right? And so any topography that I have that's sort of embedded in that underlying surface, it's going to influence the way that my material is going to set up. And so I also have to kind of consider that when I think about what's happening with my system, is that underlying surface is also, in a sense, an initial condition to my process. Okay, and then I have multi-physics. So this goes back to that, these complex multi-dimensional systems. And so I want to think about, here's this, let's see if this will play. Here's the example, right, where I'm setting up on a surface. And you can see that because I have that sort of dip, I'm going to settle into that space. That makes sense, right? That's what a liquid wants to do. That's going to look very different than if that were flat. So the governing physics, they're complex. What we wanted to do is to kind of be able to think about how to simplify these down so I could maybe write them as a simple ODE. I want to put them into this model-based control strategy. So I want to think about how to capture what I need to capture and yet not have this overly complex model. And so that was where we were sort of trying to think about how to do that. And we're going to see our learning framework in just a sec. So here's our control, right? Here's our objective. So we have some reference that I want. I'm gonna pose this reference as these, sort of stacked layers of very controlled thin film of materials. For my input, it's actually what I'm setting here is what's known as my pulse width, which I'm using a pulsed signal. So that's how long I'm going to remain open. That controls volume, right? That's the amount of material I'm releasing. It's also connected a little bit with my voltage that I'm going to apply. And so that's the baseline and then the high peak. Both of those are going to be related to how much material I lay out. So that's my volume. And then the pitch, which is the separation between them. Okay. And that's what I ultimately need to be able to control. I have my plant, which is my system. And then I have some output that I ultimately need to be able to measure in some way. So we're going to use an integrated AFM. And then here's what we currently do, right? If there's a person who's our controller who then retunes and redesigns, and we want to change that to a control system. So we have, to reiterate, we have high-speed temporal dynamics, high-resolution spatial dynamics. We're not going to do real-time sensing, but we are going to do some sensing that will term still in situ, but it's going to be layer by layer. Okay, not actively while we're printing. Of course, I'm going to have unmodeled dynamics because I'm not going to capture the complexity of the model, but I'm going to try to reduce that down into what I need, then can still put within a model-based controller. So all of that led us to, we can't do real-time feedback, but now could we think about that we have this repetitive behavior, and can we use that to control iteratively? And that's where we're going to come into our learning. So here's where we're applying learning to this example. So let's go back to our closed loop system, okay, and take just a quick second to think a little bit about what that controller, the person right now, what they have currently been doing, right? And what they've been doing is they've essentially been spending months of time to come up with these relationships between what are our control signals, right? So what are going to be, sort of my pulse width and maybe the pitch that I'm going to set, and how those are going to be related to behaviors that I want, like how flat does it set up? How smoothly does it set up? How thick does it set up? And so I need that information, because remember, the physical pattern that I create is what actually creates the refractive index, which is what creates the functional behavior. Okay, so that's really what I'm designing, but I then need to understand how my control inputs are going to be related to that. And so now what we're going to do is we're going to replace that with a learning controller. Okay, so that's a person who's been doing that. So now we're going to use a learning controller. What we wanted to do is autonomous regulation of product quality. And we want to be able to do this data validation and processing sort of in situ while we're preventing, but layer by layer. Okay, so we're going to use what's known as iterative learning control, and this is going to be applied for process regulation. So this is kind of our internal loop. So a quick introduction to iterative learning control. This is a technique that's applied for repetitive systems. It's where we take information about what we've done, so our outputs from our system, and we're going to feed that back in through some type of a learning controller. Generally, this is model-based, but it doesn't have to be. And we're going to use that information to update a control signal. Okay, and so that's a little bit different than updating the model or updating the controller itself. A couple of things that we are sort of, aware of and why we're using this. What we're after, it does have this repetition to it, which is helpful for us. We are going to assume that there are some repetitive disturbances and some model uncertainty that we're going to try to learn out. Okay, so that's the advantage of using this type of technique. And so we'll use past input and error signals to do this. So the way that ILC works, you start with your first pass, you get some error in your system. I haven't changed anything with my learning controller, so I'm setting in from a ILC perspective, I have 0 input from that control. And I have some type of error in my system. Over iterations, I keep iterating, and every time I do that, I send it through what's known as an update log, which is my learning controller. And it gives me a new control signal, which is trying to minimize this error. I can do this with 2 different types of approaches. The first is what's known as a first order ILC. What that means is I'm going to take my update law, which is what I'm sort of showing here, is going to be a function of the current input that I sent in. So that was my control signal that I currently sent, and whatever the error was that I measured. Okay, and I have some filters. That's the LF and LE, and that's what I'm designing. Okay, and that's this nice structure, and I'm only going to use the most recent information. So that's one way to do this. Another way is to do what's called a higher order ILC, and that means that I'm going to look several iterations before. Okay, so I'm going to actually take sort of this propagation of information. So not just the most recent, but actually several iterations before. I'm going to bring all that together, and I'm going to learn from that. And so I can use either of these techniques, and there's going to be some reasons why we would pick one versus another. So we go back to our control update. This is our block diagram. So this system, right, this is our system right here. Ultimately, what I have, right, is I know I have some control inputs, and I need to sort of understand how that input is related to what I'm calling my output, which is this distribution of the material in a specific location. Okay, so I want to be able to capture that and think about that as my plant dynamics. Okay, so that's like my system dynamics, only it's a little bit different than how we normally think of dynamics, which is like a time response, right? I generally think about writing, an ODE, which is a time domain dynamic response of my system. I'm going to do something a little different, where I'm actually going to think about it from the spatial domain. So instead of looking at temporally what's happening, I'm actually looking at it spatially. And I'm capturing dynamics as a function of the spread of material in a particular location. And that's really important from a 3D printing perspective, because it's not really that important that I know what happened in time. I'm actually going to try to ignore time. It happens really fast. The spreading happens really quickly. The jetting happens really quickly. And in this case, I'm focused on what's happening on the surface. So I'm not as interested in temporally what's going on. I'm really interested in spatially, because if I put a droplet here and another one here, I know there's interactions that happen. And so that's what I want to be able to capture with my model. And so this was sort of one of the initial big changes we needed to make, is that iterative learning control and sort of that framework was really done in the time domain. And so what we needed to do first was to shift it into the spatial domain. And so that changed us from having this one-dimensional dynamic into this two-dimensional impulse function. So once we've done that, then now we can go back and we can describe performance objectives. So our first one is error. And this is really going to be the geometry, right? And so we're going to be looking at what was I trying to do with my pattern and what did I actually get? And I can look at that over the whole system. And then I can also look at it incrementally from like layer to layer. And I'm going to sort of consider both because they have actually different influences on the outcome. And so I do build up my process layer by layer so I can actually capture this incremental. And I'm going to frame this in such a way that I could potentially think about looking at multiple layers back. Okay, and that's kind of the second major thing that we sort of thought about within this problem is that I actually kind of have two objectives. I want to make sure that, you know, sort of from device to device, I'm learning and I'm doing something consistently. But I also want to use the fact that I'm building up layer by layer, and I want to be able to do some learning in that dimension as well. So I'm actually going to define two learning objectives, and one is going to be learning from device to device, and one is going to be learning from layer to layer. And from device to device, I'm going to use a standard first order. From layer to layer, I'm actually going to use a higher order because I'm interested in how the layers below actually propagate and influence my performance. So I'm going to take two different learning techniques. It's the same ILC, but one of them is going to use this first order, one's going to use a higher order. Okay, and I'm going to put them together into a single architecture. Okay, and so that's what we're going to propose here. Here's our control law. So what we have is this is our cost function. We set it up as this norm optimal cost function. It is an SILC, that's spatial iterative learning control. Okay, because remember, we're now in the spatial domain. And what we're interested in is performance tracking. Okay, robustness to model uncertainty, that's the second piece. The third is my convergence rate. And so if I'm looking at the change in my control signal, then I can try to control how quickly I converge. And I generally have a trade-off with that with noise. If I'm super noisy, I can't converge really quickly. Otherwise, I'm just going to embed that noise in my learning. Okay, so I have to slow that down. Obviously, we're going to have a performance robustness trade-off standard in control design, right? And then I have this secondary component, which is where I have this convergence and noise attenuation over the layers. That's my higher order aspects, right? So the first piece is really looking from device to device. The last part with the summation, that's looking layer to layer. Okay, and so I'm putting both of them together, and then I can control how many layers down I wanna look. And what's kind of nice is if I can set it up this way, there's some really nice, already well-established rules for how I think about getting to my controller. So I just take a partial derivative and I can come up with my learning filters. These learning filters are functions of these weighting matrices, which weight how much emphasis I put on performance, robustness, convergence, and then how much of the higher order I take into account. Okay, so I can choose to just do one layer, or I can choose multiple layers. And that's what those parameters are. And I'm going to design them in such a way that I guarantee I have stability. So let's look at what that kind of looks like. So we have our update law, that's F, that's our update law, that's our control signal. Okay, and our control signal, I can separate it so that we can kind of visualize that we're looking at what's horizontal learning. So that's device to device. And then what's vertical learning, that's layer to layer. The layer to layer, as you expected, it's higher order, so it has more components to it. Okay, I can then take those and I can sort of lump them together. So I have this horizontal closed loop plant matrix, and I have this vertical plant matrix. So that's like device learning, and it's layered learning. Okay, and then I can convert this into, basically by stacking it, I can actually convert it back into what looks like ultimately a first order. I'm using blocks here because these are actually like stacked into vectors. Okay, when I do this, I now can go back to those first order ILC, which is this really nicely well-established rules on how to think about stability, how to think about convergence. And so by writing it this way, I get to leverage all of that. I do have this high dimensional F that I can also try to take advantage of. So let's talk about stability. Okay, so I'm using this first order. This is my stacked one, but I can write it this way. So this is my first order update law. When I'm thinking about stability, I'm just gonna, for right now, I'm gonna think about the case where I'm looking for asymptotic stability. So I just need the spectral radius of my F matrix to be less than 1. I'm showing F naught here. That's actually a nominal matrix. Okay, so that means I'm not gonna maybe consider all of the different uncertainties, and I'm gonna try to come up with a nominal representation. And then I'm gonna have some understanding of what the uncertainty, and I'm going to bound my behavior. Okay. And what that allows us to do is to use some of the tools that are sort of established in these domains to come up with our stability conditions. And then we just have to guarantee that we can do this within this sort of region. Okay. And that region is our uncertainty, right? Region. So I'm going to estimate a robustness radius. And as long as we can guarantee that the uncertainties that we have in our system, and a lot of these are coming from our model uncertainties that we're less than this, robustness radius, then we can guarantee that our system is going to be stable. So we need to figure out how to design this robustness radius. What I wanted to point out is the way that we think about this is we've got this nominal plant. That's what I'm looking at my convergence on, but then I have this model uncertainty. That H, which was my plant, that's my spatial dynamics, that gets embedded into this F, which is really what we're using for our update law. And so where does that come from again? Well, it comes from, again, uncertainty, right? No matter how I describe my model, and what I'm showing here is variances between different types of modeling techniques, and the error between the model and the actual system behavior. Okay, and all this was to point out really that it doesn't actually really matter. We're always going to have uncertainty in our system. But what was also kind of interesting here is one of these techniques, which is this CRNN, actually that does the best, but that's a very complicated model that I can't write in this nice contractible form to put in my learning algorithm. Okay, so what I'm going to do instead is I'm going to use some approximations like either of these to like a linear parameter varying model that's a simplified version that I can put into my system. And then I know I have some uncertainty, but I can bound that uncertainty, and then I can show that as long as I can design within that, I can be stable. And so that's what I'm showing here. The robustness radius becomes a function of your weighting gains. Okay, those are those same gains that impact that trade-off between performance, robustness, convergence rate, and what order of learning I'm using, right? So how many layers down am I using? So I get to tune those. Those are what, as a control designer, that's what I have access to, right? So if I tune those and I guarantee that I can stay within this range, then and that robustness range captures my uncertainty, then I can be stable. Okay, so let's take a quick look at some performance so that we can kind of see how this works. What we're looking at here is higher order results. So I have two examples. I have an example where we see the first layer and then where we see the fourth layer. And what we should pull away from this, right, is in the first layer, if I look at the discretized image all the way over on the right, I see a lot more color variation in the pixels. Okay, what that's telling me is there's less uniformity. Okay, there's more variation in that layer. By the fourth layer, I've actually made that fairly uniform. So the learning algorithm has done what it's supposed to do, and it's figured out what combination of input signal needs to get to where I have this nice smooth layer. Okay, and that's what I'm going for. And so that's what the algorithm is doing. That's actual outputs from that's an experimental output. Okay, so let's take a look at maybe a little bit more from a graphical perspective, what that actually looks like. So this is our layer error. So this is the error from layer to layer, which is kind of what we're looking at here. And I'm showing each color is a different layer, and it's then across multiple devices. Okay, so iteration is really device. All right, and so remember, I've got multiple devices I'm doing it. So I basically print, then we come back, we do the next layer. And we do like 10 devices, do the next layer, come back, do the third layer, come back. Okay, so that's how this is working. So obviously from the first two, really about the third or fourth, we've already sort of converged from devices. So it does a pretty fast job from device to device. And then you can also see that our layer error is getting better as we go up, which is what we see over here. One thing that's kind of interesting here that we noticed was that our layer error is doing really well. Our incremental error is actually getting worse. And so from layer to layer, our overall device error, so we're basically propagating these errors, right? And they're building up and stacking up. And even though our layer error is getting better, overall, our system is not doing better. And so we asked the question, can we do anything to try to address this? And what we came up with was actually to think about introducing model predictive control. And the reason for this is that in our examples of what we're doing, we're looking backwards, right? So we're continuously looking at what we did before, those errors in those layers, how do we use that information to design a controller? But we did not think about how does what we do now propagate forward. Okay, and that's what model predictive control allows us to do, is to think about not only do I design for what I've already done and compensate for that, but I also need to think about the fact that this material I'm going to put down in this layer is directly going to influence what I'm doing in the future. And so now can we kind of combine these so I can look backwards, use that information. I can also look forward, use that information and try to actually come up with a control signal that somehow optimizes both of those. Okay, and that's what our goal was with the model predictive control. We use a very standard model predictive control strategy here. We're not doing anything really unusual here. We measure an output. We solve a finite horizon constrained cost over n layers. We come up with a sequence of predicted optimal control inputs, and then we apply the first one. And so every layer we do this, right? And so we're using that information, but we only applied like obviously that optimal one. So we're redoing the learning in the MPC every layer. Okay, this was the motivation. I just said it, right? We want to learn from previous layers with our spatial ILC. We want to predict future layers with the MPC. And then ultimately, we want to come to a converged optimal input for the very next layer. That's what our goal was. Okay, so what does our control system look like? This was our SILC from before. So we still have that. But we also have a model predictive control component now where we're adding both a terminal cost to help improve our stability. And we're also looking at this prediction horizon, and we can design how many layers ahead we look. We can put them together into this combined cost function. And then again, we have this set of design matrices, which gives us these parameters to tune. Okay, so then how did we do? This is actually simulation results. We haven't put this on the system yet. I want to point out a couple of different things here. So what we're looking at is the layer height. That was what we looked at before, right? So now we're looking again at layer height, and we have several different cases. And the blue one is the case where all I'm focused on is making sure that my layer height does well. Okay, obviously that does the best in this case. That's what we would expect it to do. I have a whole bunch that all kind of converge right in the middle. And then I have one that doesn't do particularly well. That case is the one where I put almost all of my weighting on making sure that my overall design is good and converging. Okay, so I converge my overall system at kind of the expense of my layer to layer. And then what's interesting are all the ones in the middle, right? And all the ones in the middle is where we have the MPC included. And it becomes interesting when we look over here at the device height. Okay, and this is because the blue one, which focused on just the layers, it actually becomes unstable. And we already know that because we saw that our overall height was increasing, right? Which is not what we want. So effectively, I can think about that as unstable because I'm growing my errors in my device. But this one becomes quite interesting. This is actually one with a combined spatial ILC and model predictive control. And it does the best in terms of the device, and it's right in the middle in terms of the layer. So actually what we sort of found with this example was that when we combine them together, it ended up, if I'm interested in both of these things, right, my overall device and layer to layer, it does the best. One quick thing here, why am I interested in layer to layer? The reason for layer to layer is that with that example of that optical sensor, the consistency in the layers actually directly correlates with the refractive index. So if I'm not consistent in my layers, if I just think about the overall device, I'm not going to get the performance that I need. So it's actually really important that I'm able to do both. Okay, and that's why we needed to think about this learning framework where we could do that. Okay, so I have just a few more minutes. What I wanted to show really quickly, and I'm going to go, I'm sorry, I'm going to kind of fly through this last part, was to tell you one other little step that we're working on with this that's kind of really interesting. So the first part was what we actually call our inner loop. Okay, that's really trying to get the regulation of the process, right? And I want the process to be consistent. I want to be able to create this nice output that I have. And that was my goal. Okay, and so we designed this nice combines iterative learning controller with the model predictive controller, and it does quite well. I want to go back to that initial comment that I made, which is one of the key pieces here is that I actually need to understand what design properties I need to initially set to my system to actually get this functional output. So I was assuming that I knew what layer thickness I needed, and I knew that layer thickness because I'd already done all this pre-work to say, okay, if I do this layer thickness and then this layer thickness, these are actually two different materials. If I stack them in these ways, in these very controlled manner, I'm going to get this color. But the question that we then said, well, how do we actually get to figure out what those thicknesses should even be, right? Now I know my process can regulate to get me that thickness, but now I have to ask the question, how do I know what the thickness should be to actually get this output property? Okay, and what we had been doing again was sort of putting a person there. And what we wanted to look at was, well, could we bring some other learning, maybe think about this from a machine learning perspective and see if we could come up with some interesting ways to do this. And so what we were trying to do was to automate this process structure property relationship. Okay, so this is now a different objective. I know inside I can control to get to, once I know what I'm supposed to be hitting, I can do that. Now I need to work on the part of what should I actually be trying to target. And so that's the process structure property relationship. And what we are looking at is reinforcement learning to help us sort of come up with what this might be. Okay, and this is a collaboration with Ohio State. So really quickly, right, with reinforcement learning, the idea is that I have some idea about what that design property might look like, what I need to maybe set my design criteria. I would send it into my system. I would print with the system and I would see, you know, I'm assuming now that the system actually gives me what I ask. I ask for 100 nanometer thickness. It gives me 100 nanometer thickness. Then I actually look to see, well, did that do what I wanted it to do from a functional perspective? And if it does, I get some kind of reward. If it doesn't, I get less reward. And so then I change what I'm going to do as an input and I send it back. Okay. The problem with this is it's really expensive from a manufacturing standpoint. Okay, it takes a lot of time. It takes materials, yes, but really actually it just takes actually a lot of time. Okay, because reinforcement learning requires usually a lot of data. And so I need lots of iterations and I don't necessarily know where in my design space I need to be. And so we wanted to think about, well, could we do something that is a little bit smarter where I know quite a bit about my system. So can I design a simulation environment where I can actually do a lot of this learning? And then can I transfer that to my physical system, get some data points in here, go to some very strategic locations where I'm expecting to see good behavior, not only learn how my system's doing, but actually also learn what I didn't know about my process, right? Some uncertainty that I maybe had, or some dynamics that I wasn't considering, that now I'm going to improve my simulation environment and continue this kind of process. So we want to use RL in sort of both cases, and we want to be able to transfer knowledge between. So this is this sort of transfer learning framework in the process of manufacturing decision making. Okay, so why is this something that was kind of really exciting for us to be thinking about? Well, remember the brute force method and my poor student who had to sit there and come up with and figure out all these nice properties that they did. That's months of work, right, to get to that and to figure out what those should be. And if we can put it into this sort of automated system in a matter of hours, we can actually come up with this nice learned reward model that tells us in places in terms of parameters, process parameters that I should be selecting to kind of go into good design spaces. Okay, and it sort of gives me a sense of where should I not go and where should I probably go and take a look at. And that is a huge amount of difference in terms of time. So there are some things that are a little bit, of a challenge, obviously, within this. Of course, as we've said along the whole way, right, your models are not exact. So there's things that we're ignoring. There's things that we're not doing. So even though I might expect a certain behavior, and I'm showing an example here where this was actually an acoustic example. Okay, so that's why we're seeing bandwidth and we're seeing frequency. We're actually, instead of an optical example, this one was acoustic. So that functionality was an acoustic response. Then when I take what I learned in my simulation environment and I go and I put it on my experimental system, obviously it doesn't look quite the same. Okay, so I might have been designing for a certain spectral response and it's a little bit shifted. So again, that means that I really need to think about, can I use some of this knowledge to come back to my environment and fix that environment? And can I also use some learning within and just hope that I started in a reasonable location where I can come back to some local optima in that area? So we did apply this. In this case, we did it with an extrusion system. We went to extrusion because it's a little bit bigger. Acoustic responses are larger dimensions. Okay, so it's a lower resolution than an optical. So this is a system that was actually built in Ohio State, and the design properties where we wanted to have a peak frequency and a certain bandwidth. Okay, so that's what we were trying to do, and we were designing over what should the diameter be of the material that we're putting down, and what should be the length. Okay, and I want to know what those properties are so I can hit this output response, right? This functional behavior. What's kind of interesting is to take a look at some just other basic learning strategies, right? And kind of get a sense for how are we doing in terms of some of these other sort of off-the-shelf state-of-the-art methods that I can think about. So we combine them with a bunch of other learning techniques, just as comparison. And there's one in particular I wanted to point out that's kind of, it was interesting for us to see, was that we were looking at a Bayesian optimization. That's a very common sort of like classical way to think about dealing with this uncertainty. Okay. What was interesting is that when we brought this into the manufacturing domain, it actually didn't do very well. And there's a specific reason why. And it's because in this particular environment with additive, when I picked certain design choices, I might actually build nothing. Like it literally returns just garbage. Okay, so I didn't gain any knowledge in that design choice. So I didn't actually improve my understanding of the system at all. Okay, I didn't reduce my uncertainty. I didn't gain any information really about it because those design choices ended up putting me into a domain in the 3D printing space that didn't create anything. And so what was interesting is that the method that we were proposing, when I take my understanding of this system, I run it in these simulations where I have this sort of physics-based knowledge of what's happening, and then try to transfer that, we actually did much better in terms of our reward model and what we sort of got out of our artifacts. So this was really exciting preliminary work. These were results from obviously a combination of the simulation experimental environment, and we're continuing to work on this and apply it back to the E-jet process, which is the jetting process we were doing before. So just to sort of summarize, right, we had our inner loop, which was our process regulation, where we were using, more of a control learning based approach. We had our outer loop, which was our relationship between our process and our property and our design features. And for that, we were going to use some machine learning. And so we actually have lots of applications of learning in this space. So we specifically talked about control design. For learning control, we talked about functional device design. That was the AI. Actually, of course, we used model identification and sort of updating of our model. And we did that kind of in the beginning. And I didn't talk a lot about our modeling, but that's one of the things that we do there. Another interesting place that we didn't, again, talk about was that you could also think about learning in the context of anomaly detection, classification. So helping to understand when we do see a fault, what might have been the cause of it, and can we use that to improve our performance or even improve our understanding of these process design parameters. And that, of course, can also lead into information about in situ quality control. One of the key things with additive manufacturing is being able to verify that your part, it has high quality throughout. And so this concept of doing this layer to layer scanning and information actually gives us a map of how we did across the whole build. And that's actually something that can be very helpful in certification of these products at the end of the day. So it's not only good for control, but actually it's really good for like a company who needs to verify their part. Okay, so there's lots of open control questions continuing to work in this area, performance and robustness guarantees when we have these combined techniques, other robustness requirements when we're doing automated model updating, and then of course, uncertainties associated with defects. So that's all I have for you today. So thanks for your attention. Really quick, I also wanted to plug, there is a conference, it's in control technology and applications. I know the deadline's next week, but if you have something that you think you can roll around and do it, I'd like to just let people know that that is happening and that deadline is next week. So thanks.
Have a couple questions?
Yeah.
How far are we from using these ideas for printing 3D robots like dogs and cheetah that are mixed of soft and hard pieces, not just rigid, and they have the electronics getting closer to the growing, biological.
Right. That's a really good question. So the question is, how far are we from automating a manufacturing growth of a robotic system that's a combination of hard and soft? What I would say is that there is a significant amount of research where folks are looking at the moment in just purely combining the techniques, right? So combining the sort of hard material, soft material, printing, machining processes together. I think that first piece needs to be solved a little bit before we get to where it's fully automated and the system can kind of learn. But I think these tools that we are developing along the way are hopefully helping to kind of be building blocks towards that. Because, we're showing one process where we can, do one thing, or we're showing one example with it, but what's really nice about it is that the system itself is learning how to print what we want. And so we were giving it, at the end of the day, right, what we give it is we say, this is the functional behavior we want, go. And then the system now is learning and it understands the relationship between, the geometric output and a functional response. And now it's trying to build towards that. And, I think that's actually pretty exciting. And we need to couple it with other components now when you start thinking about, how would you build an electronic also within some soft material that can actuate and do something. But we're not there, but hopefully, like I said, we're getting building blocks towards it.
My lifetime.
Yes, Monty, you're so young, of course, in your lifetime.
Yes.
Anything else?
So my
Yeah.
question might be related actually.
Okay.
I was just expecting that when you're doing multi-material layer to layer.
Yeah.
You have a need for a certain thickness of each layer.
We do, yeah.
You didn't talk about that first?
I didn't, you're right. Yeah, I simplified the description of it, but you are absolutely correct. In that example, we actually are learning the two different. So we have two different processes we have two different spatial dynamic models because the materials behave differently. And then they have different objectives. And so we're just combining them, and it really is one learning algorithm, but in a sense, it's sort of two that are trying to work. But what we had to realize is that we needed to understand how this material set up on this other material and then vice versa. And what was really interesting is that interaction is not the same at all. So if you have this material as a nice thin film and you want to put material on top of it of a different material property, that thin film with this material on top of it doesn't behave at all in the same way. So you have to be able to model both of those and capture that within your model. But you're right, that we were actually doing it for both, but I just didn't explain it. Yeah. Any other questions? Okay.
Sure.
Thank you.
Round of applause again. So right twice in a row, so maybe I'll.
I know, that was very good.
Yeah. Usually, pull this down.
Yeah, I mean.
I think, I know, absolutely, I know. Yeah.
Yeah, one. But apparently they did take part.
Yeah, they did.
Well, yeah, I mean, how to.
Not doing anything.
It doesn't affect you guys.
You guys.
Integration, but you didn't want that.
It doesn't feel very good. Jason seems to really want that. He was recommending. I know.
They really want it. I know, on one hand, Jay says that we really want this map for native projects. On the other hand, the architects keep thinking.